Uh, Good evening, everyone. I think everyone is here. If somebody joins in between, we will uh, just revise the things what we have discussed. But we will start the session now. Thank you for joining. I'm Rahul Chaudhary. I am a PhD scholar from IIT Madras, and I am a PMRF NPTEL TA for the course Analysis and Design Principles of Microwave Antennas. Uh, this is our fifth live problem solving session. So here we will be solving as usual some problems which are related to this week's lectures, and the idea is those problems should help you to solve the assignment problems for this week. So let's start with question 1, and if you have any doubt during this when I am solving the equation, you can unmute yourself and ask the doubt. So question 1 is a Yagi Uda array of linear element is used as a TV antenna receiving primarily channel 8. So it's receiving a channel number 8 whose center frequency is given as 183 megahertz with the regular resonant lambda by 2 dipole as the feed element. In the array, the input impedance is approximately 68 ohms. The antenna is to be connected to the TV using a twin LED line with a characteristic impedance of nearly 300 ohms. So at the center frequency of 183 megahertz, what should be the smallest input impedance of the array B if it is desired to maintain a VSWR equal or less than 1.1. And in part B, what is the best way to modify the present feed to meet the desired VSWR specifications? Be very specific in explaining why your recommendation will accomplish this. So in this question, a Yagi-Uda antenna is being used for TV reception for channel number 8 whose center frequency is 183 MHz, and the driven element is a regular resonant lambda by 2 dipole, and whose input impedance is 68 ohms. So the antenna is to be connected to the TV using a LED, twin LED, means it is using some 2-wire cable, not a coaxial cable, to connect to the antenna. Suppose this is a Yagi-Uda antenna and this is a driven, and it's so what that driven element is, it's a regular to a lambda by 2 dipole whose input impedance is, let's say Z in or R in, is 68 ohms, and this characteristic impedance of this cable is, which is a twin LED cable. Twin LED cable means there are two wires, parallel wire cable, whose characteristic impedance is 300 ohms. Now our goal in this part A is we want to find out the input impedance Z in or R in min, means what should be the minimum value of this thing if we want to have a VSWR less than equal to 1.1. VSWR means a voltage standing wave ratio, which is related to the reflection coefficient. So first the idea should be we want to find out the reflection coefficient value ranges, like what if it has to be less than equal to 1.1, what are the ranges for lambda reflection coefficient, and from that we can find out this Z in or R in, the minimum one. So I hope the question is clear. Now if it is clear, then we will move on to the solution for this question number 1. So first the center frequency of channel 8, that is a desired channel that we want to receive using the Yagi-Uda antenna. So the center frequency for this is given as 183 megahertz, and the wavelength from this we can find out C by F, which is approximately equals to 1.64 meters. So Z in is given as 68 ohms, which is the feed for the feed element, that is lambda by 2 resonant dipole. What is it? Is it that's a lambda by 2 dipole, and the characteristic impedance of the cable, that 2-wire cable, is given as 300 ohms. This is for the transmission line. And it is desired to have the VSWR less than equal to 1.1, and we know VSWR formula is 1 plus gamma divided by 1 minus gamma, where gamma is the reflection coefficient. Means definitely if there is a mismatch, if this is a transmission line which is connected to the antenna element, if they are not perfectly matched, then there will be reflection. Some of the power will be transmitted and some of it will be reflected. So but now it is desired to have VSWR of less than 1.1. So based on this we can find out what the ranges of the gamma is, what are the allowable ranges for gamma, that is PSWR is 1.1 is equals to 1 plus divided by 1 minus gamma. So this can be, we can take this denominator to this side and multiply it with 1.1. We will get 1.1 minus times gamma is equals to 1 plus gamma. So which will give us 1.1 is equals to 0.1 is equals to 2.1 times gamma. So gamma will be 0.1 divided by 2.1, which comes out to be 0.0476. What it means that the maximum gamma can be, or it should be less than 0.0476. If we want to have a PSWR of 1.1, then gamma has to be less than or equal to 0.0476. Now in the problem we have to find the minimum Zin, and we know how that characteristic impedance of a transmission line and load impedance are related with reflection coefficient. So gamma is equals to, since it is real here, Zin, I am just writing Zin as R in minus Z Z0, the characteristic impedance of the line, R in plus Z0. So that has to be less than or equal to 0.0476. And Z0 we already know it's fixed, like it has to be 300 ohms. But now we want to find out what is the minimum value of R in, so that we can have this PSWR less than 1.1. So R in minus 300 ohms divided by R in plus 300 ohms, which has to be less than equal to 0.0476. R in, I can rewrite this as 0.0476. Since the whole thing is positive, so I can take out this modulus. So because we know that resistance is not going to be negative, definitely it's positive, and then plus 300, it's already going to be a positive value, so we can remove the modulus on this side for the denominator, plus 300. Now if we look this, there are two possible cases here. So there are two possibilities here. Here two cases are possible. Case 1, when the input impedance of that antenna is less than 300 ohms. When Rin is less than 300 ohms, that means this Rin is less than 300, this thing all going to be negative. So I can write this as, if you want to remove the modulus, you have to put a negative sign here. So I can rewrite this as 300 minus Rin has to be less than equal to 0.0476 times of Rin plus 300. Now when we solve this, we will get 300 minus Rin less than equals to 0.0476 times Rin plus 14.28. So what I did, I have multiplied this 0.0476 with Rin and 300. So now I can take this and rearrange it and rewrite this as 285. if we take this 14.28 on the left hand side, we will get 285.72, which should be less than 1.0476 Rn. So in this case, Rn should be greater than or equal to 272.6 ohms. And case 2, then the input impedance of that feed element is greater than 300. In that case, this modulus is going to be positive. So yeah, correct. So I can simply write this as R in minus 300, which will be less than equal to 0.0476 R in plus 14.28. So I can rearrange it and rewrite this as 0.9524 times R in should be less than equal to 314.28. So we will get, in this case, R in should be less than equal to 330.2 ohms. So based on this, we will get, we got a range of R in values, which will result in VSWR less than 1.1. So what is that range is? That is 272.6 ohms. So R in lies between 272.6 to 330.2 ohms, and thus the smallest input impedance of the array in the sense Yagi-Uda antenna is also, it's a parasitic array, right? Because in the lectures we have seen that only one element is driven, or means there is one feed and the other elements are not fed. So that's why those are parasitic elements. So a Yagi-Uda antenna is an array. So thus the smallest input impedance of the array that will keep VSWR less than or equal to 1.1 is, now simply we have to select the least value possible. So this is the least value, right? The least value, which is the smallest input impedance, is 272.6 ohms. So this is a solution for part A of question number 1. I hope this is clear. If you have any doubt in this, please let me know. Then okay, if it is clear, then we will move on to the second part, part B. In this part, what is the best way to modify the present feed to meet the desired VSWR specifications? So now it's asking about the particular or practical solution to that problem. So what is the best way to modify the present feed? So currently we have a lambda by 2 dipole as a feed, and if you want to make it, now we know what the input impedance of that antenna or the feed should be. It should be 272.6 ohms. But how to do this? How to make this lambda by 2 dipole whose input impedance is 60 ohms into this? So that's what the question is asking. So we have already seen folded dipole, right? So the best way is to use a folded dipole. The best way is to use a folded dipole as the driven element or as the feed. So a folded dipole antenna is formed by adding a second conductor parallel to the dipole and connecting it at the ends and for two identical wires with same diameter, the input impedance is approximately that's the whole idea, right? We want to remove like increase the input impedance. So for a folded dipole, the input impedance is approximately 4 times that of the simple dipole. That means it will be 4 times of 68 ohms. So the input impedance of that folded dipole will be 4 times of 68, which is 272 ohms. So this is almost exactly within the required 273 to 330 ohms range that we calculated, right? It's approximately very similar, just 1 ohm difference is there. For VSWR to be less than equal to 1.1 with a 300 ohms transmission line. So what we did is, what we have to do is to suppose this is the lambda by 2 dipole, so we have to connect a same diameter cable in parallel to the dipole, so that will make it as a lambda by 2 folded dipole. So now this is a lambda by 2 folded dipole as the driven element for the Yagi-Uda antenna. If you want to have a VSWR less than 1.1. I hope this is clear. If you have any doubt in this, please let me know. If question 1 is clear, then we will move on to question number 2. In question 2, in a log periodic array, if the fundamental frequency is 1, f1, what would be the frequency of the third element in terms of tau? So we know that tau in the lectures, a professor told us tau is the log period, and it is related to the subsequent frequency as, suppose fn plus 1 will be tau times of the previous frequency, means fn. So this is the relationship between this log period and the frequency. I hope the question is clear. So in this problem we have to find out the frequency of the third element in terms of tau. The fundamental frequency f1 is the frequency of the first element. What would be the frequency of the third element in terms of tau? So in a log periodic array, so a log periodic array looks something like multiple elements are there. So this is what a log periodic array looks like. Array the resonant frequencies of the elements follow fn plus 1 is tau times of the previous element fn. So where f1 is first element, so f2 will be tau times f1, and the third element resonant frequency for the third element is f3. This is for the third element. So the f3 will be tau times of f2, and if we write it in terms of f1, which is f2 is tau times of f1, which gives tau square f1. So now this is the required answer. Now we will match with the given options. So the correct option is B. So the correct option is option B, tau square f1. So I hope this is clear. If you have any doubt in this, please let me know. If question 2 is clear, we will move on to question number 3. So in question number 3, two statements are given. Statement 1 is the reflector element in a Yagi-Uda antenna is typically longer than the driven element, and statement 2 is longer reflector element helps in improving the forward gain by reflecting the back radiations towards the driven element. So if you read carefully, both the statements are true. And statement 2 says that longer reflector element helps in improving the forward gain by reflecting the back radiation towards the driven element. So this is the reason why the reflector element in the Yagi-Uda antenna is typically longer than the driven element. So now we will read all four options. Option A is both statement 1 and 2 are correct. Yes, we know both are correct. And statement 2 is the correct explanation of statement 1. Yes. That's why the reflector element is longer, because longer reflector element helps in improving the forward gain by reflecting the back radiation towards the driven element. So statement 2 is correct, and this is a correct explanation of statement 1. Option B, statement 1 and 2 are correct, but statement 2 is not correct. No, the option B is not true. Or neither C and D. So only the correct option is A. So the reflector element in a Yagi-Uda antenna is longer than the driven element. In a So that's what a Yagi-Uda antenna looks like. This is the reflector, this is the driven element, and these are directors. So the driven element will always be less than the reflector, because whatever the backward waves are, it will reflect back towards the driven element, which will help this antenna to have a higher forward gain. The reflector element in a Yagi-Uda antenna is longer than the driven element to reflect the back radiation towards the driven element, thus improving the forward gain. Hence, both statements are true, and statement 2 is correct explanation of statement 1. Is correctly explains statement 1. So the correct option is option A. Now we will move on to question number 4. So the data for question number 4 and 5 is common. Question is, a log periodic array has 5 antenna elements. The length of the first antenna element is 3 meter and it is operating at 100 megahertz. The ratio of the diameter of the two adjacent elements is 3. So the ratio of the diameter means an plus 1 divided by an is given as 3. So, and we have to determine the length of the third antenna element in terms of lambda naught. First element length is given as 3 meters, and now we have to find the length of the third element for a log periodic array which has 5 antenna elements. I hope the question is clear. So it's given. Now first we will note down what are the given values in the problem. In the problem we have given a log periodic antenna with number of antenna elements as 5, and length of the first element L1 is given as 3 meters, and the operating frequency the first element f1 is given as 100 megahertz, and also the it's given that the ratio of diameter is 3. Now free space wavelength will be, now we can calculate the wavelength for the first element. Free space wavelength is lambda naught, means the wave is traveling at the speed of light, c by f1 into 10 to the power 8 divided by 100 megahertz, which gives 3 meters. The free space wavelength is also 3 meters. So L1 is 3 meters, and so is lambda naught. Now for a log periodic antenna, the ratio of the length of the next element to that of the previous element, Ln plus 1 by Ln, is also the ratio is same as the ratio of the diameters, which is tau, which is given as 3. So Ln plus 1 divided by Ln has to be 3, and we know that L2 by L1 is also 3, and we know L1 is given in the problem as 3 into 3, that means L2 is, or in terms of lambda we can write, because in the options only lambda naught is given, the lengths are given as a multiple of lambda naught. So we will take L1, we know L1 is 3 meter, which is also equal to lambda naught, so we will write L2 comes out to be 3 times of lambda naught. Now L3 will be equal to 3 times of L2, and L2 we know that is 3 times of lambda naught, so L3 will be 9 lambda naught. Now if we match it with the given options, so option C is correct. So correct option is C. So correct option for question number 4 is L is equals to 9 times of lambda naught. Now in question 5, for the same problem, we have to determine the frequency at which the last antenna element is operating. So like this log periodic antenna is something like these 5 are there, and we have to find out the frequency at which the last element is operating. So given the operating frequency of the first antenna element f1s 100 megahertz, so the frequency of the last antenna element is given by frequency of the last antenna element is given by the last element is f5. The 5 elements are there, so f5 will be f1 times of tau to the power 4, which is 100 into tau is 3 to the power 4 megahertz, which is 8100 megahertz, or we can write in terms of gigahertz as 8.1 gigahertz. So this is the frequency of the last element. So now we will match it with the given options. So here the correct option is option B, 8.1 gigahertz. So correct option is C. If you have any doubt in question number 4 and 5, please let me know. If it is clear, then okay. Okay, I will show you the question number 3. Sorry, I didn't show that. Okay, so question number 3 I can repeat again if you want. There are two statements and we have to select the option. Which option says that both statements are correct, and statement 2 is a correct explanation of statement 1. So it says these two statements are regarding the Yagi-Uda antenna. So I explained it that the longer reflector element helps in improving the forward gain by reflecting the back radiation towards the driven element. That is the reason why the reflector element in a Yagi-Uda antenna is typically longer than the driven element. So if you just, I hope this is clear. If I just simply search for a log Yagi-Uda antenna, earlier people have used them for that TV reception. It looks something like this. That's what a Yagi-Uda antenna is. And if you see that the reflector element is always longer, this is the reflector element, it's always longer than the driven element. So in this, only one single element is the element which is fed. So these are dipole elements. Only element which is fed is the driven element, and the rest are just to get the directivity better. And the gain also, the gain is better than a normal dipole antenna. That's why this was being used earlier for a single channel reception, but we can't have a multiple channels, and then the quality will that won't be good. So that is the reason now we have the dish antennas. And the frequency also was, the operating frequency was less here. So that's what dipole antenna, that Yagi-Uda antenna looks like. And if you see in this one, the driven element is folded, so that's why that they have folded it in order to match it with the transmission line. So this is a folded dipole element. All are dipoles, but the feed is folded here. Then there are two parallel lines, that's why. I hope the question 3 is clear. Now we will move on to question number 6. Question number 6 is bit mathematical. If you have seen the lecture regarding the derivation of aperture antennas, where sir has introduced a Fourier transform, and like why do we have to do that, you can explain, like you can understand this problem better. So it's just a purely mathematical question here. If Fourier transform of f of kx ky is equals to minus, that Fourier transform formula is given, represents the special Fourier transform of a wave x and y, then the value of this integral will be, based on these four options we have to select. If you look carefully, this is like the half part of what for reverse like inverse Fourier transform will look like. Only the element which should have been there is 1 by 2 pi square. In this one I am talking about. Then the value of this will be, okay, I will write it down here. Now we are solving question number 6. It is specified that this function f of kx ky is minus infinity to infinity is a Fourier transform of this function f of x and f of y. F of so here they have forgot to put the f of x and y because it's a represents a special transformation. It's varying with x and y both. So it should have been written like f of xy into e to the power j kx dx dy. And we know that f of x ky is minus infinity to infinity and minus infinity to infinity, f of kx ky multiplied with the complex conjugate of g of this is another function which also varies with kx and ky into e to the power minus j k of x into x plus ky into y dkx dky. Now using this Parseval's identity, we can write that minus infinity to infinity and the integral between minus infinity double integral of f of xy dx dy as 1 by 4 pi square kx ky integral kx ky e to the power minus j kx ky of y into d kx d ky. Therefore now in the problem we have to tell what this is, this part. So we can take this 4 pi square minus infinity to infinity. I will rewrite this part here. Sorry, a small mistake. This also has a small g of x and y complex conjugate in the multiple of this. So it will be e to the power minus j kxx plus ky y dkx dky. Now what I have done this, I have taken this numerator denominator into the LHS side and rewrite this as, it will become 4 pi square f of xy g of xy dx dy. So it should be something like this. So I recommend you guys to watch the lecture, I guess 22 or 23. It has been explained in a much better way than I can do right now. So if you match it with the given options, for question number 6 is, then the correct option is 4 pi square, option D. I hope this is clear, but if you watch the lecture again, it become more clearer. That's what we have used a Percival's identity here to in order to find it out. Okay, now we will move on to question number 7. What is the effect of an aperture that is large in terms of wavelength on the Fourier transform of the aperture field? Okay, I will read it the question. What is the effect of an aperture that is large in terms of wavelength on the Fourier transform of the aperture field? So this problem is asking about the effect if we have a larger aperture in terms of wavelength. In terms of wavelength also means that aperture is getting larger. What will be its effect on the field in the Ex and H, magnetic or electric field? What will be the effect on the Fourier transform of that aperture field? In terms of, I guess it is asking in terms of beam width. So okay, let's start with the solution for question number 7. The far field radiation pattern of an aperture antenna, the far field radiation pattern of an aperture antenna is proportional to the Fourier transform of the aperture field distribution. The far field radiation pattern of an aperture antenna is proportional to the Fourier transform of the aperture field distribution. So a small aperture will have a broad diffraction pattern, and a large aperture will have a narrow diffraction pattern. So as the aperture size increases or grows, as the aperture size grows in terms of wavelength, the beam width of the Fourier transform shrinks. And the result is that the radiation pattern become highly peaked in the forward direction. The result is that the radiation pattern becomes highly peaked in the forward direction. That is narrow main lobe with higher directivity. So if we match it these observations with the given options, we will see what is the effect of an aperture that is large in terms of wavelength on the Fourier transform of the aperture field. Option A is it causes the Fourier transform to be uniformly distributed. No. Option B, it makes a Fourier transform highly peaked in the forward direction. Yes. Option C, it spreads the Fourier transform in all. No, that is not correct. It has no significant effect on the Fourier transform, and that is also not correct. So correct option is option B. So I suggest if you want to understand this better, you should watch, if you don't have, watch lecture 23, I guess, where sir has derived this field distribution for an aperture antenna. Then you will get a clearer idea. Now we will move on to question number 8. Which of the following statements is true for the phase error in an H-plane horn antenna? So 4 options are given, and option A is the phase error should not exceed plus minus pi by 2 at the side of the aperture. Option B, the phase error should not exceed plus minus pi by 4 at the side of the aperture, and the phase error should not exceed, option C is the phase error should not exceed plus minus pi at the side of the aperture, and option D, the phase error is negligible in H-plane horn antenna. So for a H-plane antenna, the phase error should not exceed plus minus pi by 4 on the side of the aperture to ensure proper phase distribution and maintain high directivity. So the appropriate choice is option B. I will rewrite this. The H-plane, for H-plane horns, the phase error should not exceed plus minus pi by 4 at the sides of the aperture to ensure proper phase distribution and maintain high directivity. So the option B is correct. I hope this is clear. Now we'll move on to question number 9. So the data is common for question 9th and 10th. It is desired to design a pyramidal horn antenna for optimum directivity with total flare angle of 30 degree in the E plane and 50 degree in the H plane. Assuming the dimensions of the feed rectangular waveguide are A is given as 0.5 times of lambda and B is 0.25 times of lambda. In question 9, we have to determine the horn dimensions at its aperture. That means it looks something like this. and this is the aperture. The antenna is something like this. Since it is a pyramidal horn, it has this kind of a shape. So this is the aperture, like in the front face where it is radiating. So this a dimension we have to find, a and b, a dash and b dash, both in terms of lambda. I hope the question is clear. So given in the problem, we have given that a is 0.5 times of lambda and b is 0.25 times lambda, and the flare angle in direction of E field is, so psi E is, so I am denoting this as the field angle in the E plane is 30 degrees, 2 psi is 30 degree, and in the H plane it is 2 psi H is given as 50 degrees. So these are the data which is given in the problem. Now we have to find out the dimensions at its aperture. That means you have to find b prime, which is approximately equal to, I am directly using the formula here. So the explanation, the derivation of these formulas is given in the lectures and in the textbook. So b prime is approximately equals to 2 under root 2 lambda rho 1, and psi e is tan inverse b prime by 2 by rho 1. So now based on using this equation 1 and 2, we can write rho 1 as b prime by 2 divided by 10 15 degrees, because 2 psi is 30, so psi is 15, so we taken this tan inverse is 10. Now when you solve this, b prime by 2 divided by 0.1015 is 15 degrees is 0.2679. When we solve this, we will get 3.7321 times b prime by 2. Therefore b prime square, if we take square of this on both direction, it is 2 lambda rho 1. Now we will replace this rho 1 in terms of b prime by 2, and we will get 2 lambda times 1.866 b prime. When we solve this, we will get 3.7321 into b prime into lambda, or we can write in terms of b as b prime comes out to be 3.7321 times lambda. Now we can do the same thing again for a prime. A prime is approximately equals to under root 3 times of lambda into rho 2, and psi h is equals to tan inverse a prime by 2 divided by rho 2. So now we'll take this tan inverse to this side and our left hand side, and row 2 we can write down as a prime by 2. Wait a second. So we can write this row 2 as a prime by 2 divided by tan inverse, because you have taken this tan to this left hand side, and tan psi h we know is 25 degrees. So a prime by 2 divided by tan 25 degrees, and when we solve this we will get a prime by 2 divided by tan 25 is 0.4663. So we can now write this as 1 divided by 0.4663 is 2.1445 multiplied with a prime by 2. Therefore a prime square is 3 lambda times row 2, and I can substitute this row 2 in terms of a prime, which is a lambda into 2.1445 times a prime by 2, and when we solve this we will get a prime as 3.2166 times lambda. So now we have the values for this aperture dimensions a prime and b prime. Now we'll compare it with the given options. So here the correct option is option D. So I hope this is clear. I am not going to derive the formulas, I will just directly use the formulas. You can refer to the lectures and textbook. It has been explained clearly why these formulas are like this. Now we will move on to question number 10. Determine the other Hone dimensions row 1, row 2, row E and row H, all in terms of lambda. Now we will start solving question number 10. So in the previous problem we can from this we can write, because the data is common, right? So row 1 is 1.866 times b prime. Now we know what is the value for b prime is. The value is 3.7321 lambda, which is 6.964 times lambda, 641 times lambda. And row 2 also we can write, which was 1.0722 times a prime, which is 1.0722, and a prime was 3.216666 lambda, and when we multiply this we will get 3.4488 times lambda. Now we have to find out row E and row H. So row is given by this formula for a horn antenna is row 1 square plus b prime by 2 whole square, which comes out to be, so lambda will take out as row 1 is 6.9641 whole square plus b1 is b1 by 2 comes out to be 1.866 whole square, and when we solve this row E comes out to be 7.2098 times lambda, and row H comes out to be, and the formula for row H is under root row 2 whole square plus a prime by 2 whole square. And similarly we will take the lambda out, because the lambda is there in both of the terms, row 2 and a prime by 2. So now row 2 is 3.4488 whole square plus a prime by 2 will be 1.6083 whole square. So when we solve this, we will get rho h as 3.8054 lambda. So now we got all the required values. Now we'll match it with the given options, and the option, if we match it to the option C is correct, because lambda h should be 3.81. We can write this 3.080 as 3.81, approximately equal. Rho A is 7.21 and rho 2 should be 3.45 and row 1 should be 6.96. So correct option is option C. I hope this question is clear. The only thing is we just have to remember the formula and use it. It's a directly formula based numerical problem for question number 9th and 10th. Now we'll move on to question number 11. A rectangular waveguide of dimensions 1.91 cm and 0.95 cm is operating at 12 GHz in dominating mode. Now we have to determine the directivity of the aperture. So the directivity of a rectangular waveguide can be found using the formula D is equals to 64 times A into B divided by beta TE10 times lambda cube, and the operating frequency we know is given as 12 gigahertz. The operating wavelength we can find out by C by F, 12 into 10 to the power 9. When we solve, it comes out to be 0.025 meters. Now from this we can calculate beta TE10, which is pi times 4 by lambda naught square minus 1 by a square under root. So I am writing it as 0.5. So now when we solve this, lambda naught we know 0.25 and E2 is given in the problem is 1.91 in centimeters. So when you substitute this, we will get 190, and hence now we can calculate the directivity as 64 into, I am writing this in meters, 0.0191 into 0.0095 meters divided by beta TE10 comes out to be 190 into lambda cube, which is 0.025 cube. So when you solve this, you will get 3.9. So when we match it with the options, the correct option is option A. I hope this is clear. This also is a simple problem based on the formula. So that's all for today. If you have any doubt, please let me know. Otherwise, that's all for today's session. We will meet on next Saturday, same time, on 27th. Thank you for joining. That's all for today. Thank you.
Thank you, sir.